All right, hello and welcome back, guys. In this video, I'm going to be taking you through the solutions to this week's SAC preparation questions, which all have to do with smooth and continuous functions, and specifically piecewise functions. So, starting out, we've got the first question here. The stylus isn't working. There we go. So the first question here, it asks us, what does it mean for a function to be smooth or continuous? I'm actually going to start with the second part here. So what exactly does it mean for a function to be continuous? Well, we can say that the definition is something along the lines of we can draw the function without lifting our pen off of the page, or we could say that the function does not have any points of discontinuity across its domain. So I'm just going to write that kind of definition. So if a function is continuous, it will, let's see if we can put this into words. So we can say a continuous function is one that does not contain any points of discontinuity. And what I mean by that is that I can draw the entire function without lifting my pen off of the page. Now the next question is, what does it mean for a function to be smooth? And essentially you can think of this as if a function is smooth, it does not have any jagged edges, or in other words, we would say that if we were to take the derivative of this function, so if the function were to look like, make a larger one over here, the function were to look like that, so there's like a linear equation and then there's maybe like a quadratic equation for this part of its domain over here. Quadratic equation like that, we would know that the derivative of a linear equation is going to be like a straight line. So if this is a positive line here, then its derivative is going to be a positive number, and the derivative of this this parabola here is going to be a linear equation. So for this part of the function's domain, what I'm sketching here in red is the derivative function. The derivative is constant, and then for this part of the domain, the derivative is linear. And we can see that this might not necessarily be continuous, so therefore we would say that in order for a function to be smooth, the derivative function needs to be continuous. So a function is smooth if and only if, so I'll write that, a function is smooth if and only if its derivative is continuous. And one way of thinking about this is, like I said, there's no jagged points along the graph. Another way of thinking about it is if we were to take a piecewise function, look at its endpoint, and look at the point, like the point of its endpoint, whatever the x value is, if I plug that into the first equation, I'm going to get a number. If I plug it into the second equation, I'm going to get another number. If those two numbers are the same, then the function is smooth. So we need to draw a graph that is smooth and not continuous. That's actually impossible, so I'm just going to swap those two words around. So we need to draw a graph that is continuous and not smooth. So what would this look like? Well, we can say that continuous means we can draw it without lifting our pen off of the page. So we'll start using maybe a red color. I want to draw maybe the function looks like this for the first part of its domain, and for the second part of its domain, it's a parabola. As we can see, I've drawn that entire thing without lifting my pen off the page, but as you can also see at this particular point, the function is jagged, and we can see the derivative is not equal. An even simpler example would just be a linear equation that looks like that, and then a linear equation that looks like this, so one with a positive gradient, and then one with a negative gradient going down like that. So that would be f of x. So that's y equal f of x there. Replace the y-axis over here, so this just says y. So we can say that, okay, so when y is equal to f of x, we get that particular function there. And if we were to draw maybe the derivative function in purple, if we were to draw the derivative of this, well, for the first part of its domain, it's going to be some positive number. And for the second part of its domain, it's going to be some negative number. And as we can see in the middle, this derivative function has a point of discontinuity. So therefore, this function here is smooth and not continuous. So the red function. So that is, continuous, but not smooth. All right. So hopefully we understand those definitions because we're going to now use them for the rest of the task. So starting out with this problem here, we've been given a piecewise function. The first question is going to require us to figure out what A, B, C, and D are in this cubic that we've been given here. Whenever you have a question like this, we need to somehow figure out some unknown values given some pieces of information. You should keep in mind a general rule. However many pieces of information we're trying to find, so however many unknowns there are, we need to use that number of initial conditions to find those points. So we're trying to find A, B, C, and D. So we should think, what are the 4 pieces of information that we've been given about this particular function here? What I'm going to do is I'm going to call that function maybe f1x. So I'm going to say f1x is equal to that thing there. So we're trying to solve when is f1x, which is equal to ax cubed plus bx squared plus cx plus d. What information do I know about f of x? Well, looking at these points that lie on the curve, we can see that on this curve, we can see that the point 0, 4 lines up on that curve. So that tells us if I plug in 0 into this equation, I'm going to get out an output of 4. So let's write that out. Okay, so that means if I plug in 0 into this expression up here, I'm going to get out 4. We can probably see, looking at that D needs to be equal to 4, because if I plug in 0, we'll just get A times 0 plus B times 0 plus C times 0 plus D. So therefore, D is equal to 4. Okay, what else do we know about this? Well, we can see here, we've also got this point here, 2, 6. So that tells us when x is equal to 2, the output is equal to 6. And we've also got this point here on the curve. We have the point 4, 2 lying on the curve, so that tells us when x is equal to 4, y is equal to 2. So when x is equal to 4, y is equal to 2. All right. Now, there is actually one more piece of information that's been given to us here. It says here that the function is smooth and continuous across its domain and has a maximum at 2, 6. The fact that this point is a maximum actually gives us another piece of information. What that tells us is that the derivative function at that point, so the derivative function at 2, is equal to 0, because as we know, the derivative at a maximum, a minimum, a stationary point of inflection is always equal to 0. So those are our 4 pieces of information. We're then essentially going to just use them to find what A, B, C, and D are. And to do this, I'm just going to use the CAS calculator. So to start out, let's just wipe this. So I'm going to go clear all, wipe what I was doing there last time. And then let's just start by setting this out. So start out, we're going to need to define our function. So to do that, we're going to go action, command, define. And we're going to define f of x as equal to a times x cubed plus b times x squared plus c times x plus d. All right, looking good. All right, second thing I need to define is the derivative function. So I'm going to go again, action, command define. I'm going to define g of x. So we want g of x to be equal to, well, what's the derivative of this first function? We could do that using the CAS, but I'm going to do it manually. So it's going to be 3 times x squared plus 2 times x plus c. So just for those of you following along, what I've done there is I've derived this first function here. Let's just do this in a different color, purple. So I'll just show you what I did. We're taking the derivative of this function here. So as we know, based on the power rule, this 3 is going to come out the front and the power of x is going to count down by 1. Similarly, the 2 for the b is going to come out the front here. So we're going to get 2bx, power counts down from 2 to 1. And lastly, this just becomes c. 1 comes out the front, so we get 1 times c, just c, and then the power counts down by 1. So it becomes 0, and of course the constant d, its derivative is equal to 0. All right, so this is our derivative function. So we're going to define g of x as equal to that derivative. And now I'm just going to fill in the initial conditions on the CAS. So I'm just going to create 4 lines because I've got 4 initial conditions. I'm just going to type them in. So we've got f of 0 is equal to 4, f of 2 is equal to 6, and f of 4 is equal to 2, and finally g of 2 is equal to 0. And just remember, I've just defined g here as the derivative function f dash x. Then I'm going to ask the calculator, I want to solve for a, b, c, and d, and it tells me that these are hypothetically the answers there. Always good just to double check everything is correct here. Not sure if that's right. So we've got 0, 2, 6, 4, 2, and g of 2 is equal to 0. Let's just make sure that I've correctly defined each of these functions. Ax cubed plus bx squared plus cx plus d. And we had 3x squared plus 2x plus c. That all looks pretty good. So if I go over to my answer, so this is what I started out with. No, it looks like I've made a mistake somewhere along the line. Let's see if we can quickly troubleshoot the solution. Hopefully I don't have to restart this. So the derivative, yeah, so we've got when x is equal to 2, we get 6. The initial conditions are all looking right. It's probably somewhere in how I've defined these functions. We've got ax cubed plus bx squared plus cx plus d. I forgot the a here. So that needs to be an a times x squared plus b times. Okay, so we needed to include the a's and the b's there. There we go. That gives us the correct answer. So if I just bring this over here, we can write out the correct answer is the function f1x needs to be equal to negative 1 on 8 x cubed plus 0x squared plus 3 over 2 x plus 4. All right, so there's our answer. All right, now, what does it mean to verify that the function is smooth and continuous at the point 6, 0? So first up, we've called that first one f1. So let's just call the second part of this function from the x values of 4 to 6. So that's this part of the piecewise function here. I'm going to call that f2, and I'm going to call the third one f3 of x. So we've got these two cross the boundary of x equals 6. And as we can see here on the graph, we can see that hypothetically, if this is in fact smooth and continuous, just to quickly remind you what that means, continuous means I can draw the whole thing without lifting my pen off the page. Sure looks like it's continuous. Smooth means that at each of these endpoints, there's no jagged component. So it means that the derivative on either side, so for that red curve and for that blue curve, it's the same, and the derivative on either side here is also the same. So let's check to see if that's the case. So first thing I'm going to do is I want to check if it's continuous at x equals 6. So I'm going to check continuous and then smooth. So what this means is if I plug in x equals 6 into these two equations, we should have that. If I plug it into the second equation, we should get the same answer as if I plug it into the third equation. So if I plug it into this one here, I should get, in this case, 0. And if I plug it into the third equation, I should also get 0. So I'm just going to start out with the left-hand side over here. So f2 is 7 over 4x cubed. So let's write that out. 7 over 4 x squared, I think it was. X squared, yep. Minus 37 over 2 times x plus 48. And that is hypothetically, is this equal to f3, which is 5 over 2x minus 15. And I've just put a question mark there because I don't know if this is true yet. This is actually what I'm trying to show. So let's check to see if this is true. So it's not letting me change color. There we go. So what I'm doing here is I'm going to plug in 6 into each of these equations as my input. So I plug it in there. If I was to resolve this, we're going to see that there is 7 times 36 over 4. So 7 times 36 over 4 minus, well, this is going to be 6 divided by 2, so that's going to be 3 times 37 plus 48. Is that the same as, well, this one here should be a little bit easier to work out. That's going to be 30 divided by 2. So 15 minus 15, which is equal to 0. So that right-hand side is definitely equal to 0. We might need to check this one here a little bit more closely. So first up, if we want to simplify this one down a little bit, just to try and do this without using a calculator, that's going to become 18 over 2. If I divide both the top and the bottom by 2, and then I can divide them again. So 18 divided by 2, that's just 9. So this becomes 9 times 7 over here. Yeah, and then that was 37. Yep. All right, so that becomes 9 times 7 All right, so then we're going to get 37. I think is that a multiple of 13? I think I'm going to have to unfortunately reach for the calculator for this one. So let's just see if we can double check it. So what I'm doing is I'm writing out this equation here. So this is 7 over 4 times 6 squared minus 37 over 2 times x, so times 6 plus 48. Okay, and that is in fact 0. Okay, cool. So that tells us that the left-hand side and the right-hand side is equal to 0. So that's equal to 0, that's equal to 0. Okay, so that tells us that the function is in fact continuous, but it does not tell us if the function is smooth. This only tells us that on both sides the function is the same. So to check if smooth, what do we have to do? Well, now we have to consider the two functions' derivatives. So if the function is smooth, that tells us that the derivative of the second function, so the derivative, should be equal to the derivative of the third function. So let's check to see if this is correct. So first up, we'll take our equation here and we see if we can find its derivative. So the derivative of f2 dash is going to be, well, if we think about it, starting out with this function here, let's just work it out up here. The derivatives, put them in this column over here. So we want to find the derivative of the second one. So that's going to be, the 2 is going to come out here. It's going to cancel out with the 4, and we'll just be left with 7 over 2. 7 over 2 times x, and we have minus 37 over 2. And then the derivative of this second function here is going to be simply, if we look at this one here, we're going to reduce that power of x by 1, and we're just going to be left with 5 over 2. So that's a constant derivative for that third function there. Okay, so now we can just consider each of these. If I put in an input of 6 into the first equation, so let's consider f2 with an input of 6. So that's that first one there. We're going to get 7 over 2 times 6 minus 37 over 2. So that's going to be 6 times 7, which is 42. So 42 over 2 minus 37 over 2. So that's going to be, okay, so that's 18, no. So, why is that so hard? That's 21. So 21 minus 37 over 2, which is going to be a little bit more challenging. So if we round this to the nearest number, that's going to be 18 and a half, I think. So 18 and a half. So 21 take away 18 and a half. That gives us 2.5, I believe, which is, yep, what we wanted. So we can see there that the third function, this one's derivative, f3, that was a constant 2.5. So we can see that both of them at the point x equals 6 have a derivative of 2.5. So we can see that, yes, they do have 2.5. So yes, it is both smooth and continuous. So that's how we go about checking this. All right, so now question 3 is where everything sort of comes together. We're asked to develop a piecewise function that passes through 3 particular points. So how would you go about answering a question like this? Well, the first thing you want to do is kind of come up with a sketch for exactly what you want to do. I'm going to start by kind of considering, okay, we've got these criteria down here. We need to make sure they're all satisfied. We need to have a stationary point at the point 0, -4. So this is going to be probably a minimum. And then this one here up the top, 4, 2, that needs to be a maximum. Those are the requirements we've been given. They must be met. Then let's sort of sketch how we want this graph to appear. So personally, I want maybe this one here. I want that to be a minimum of some sort. So I'm envisaging this being some sort of quadratic. We need to use a minimum of 3 particular functions to define this overall thing. So I'm going to let that be my first function. I'll find that in a minute. Second function, okay, I'm envisaging maybe this point here, this 1, 0, that could be potentially a stationary point of inflection. So let's just draw that as such. Okay, that could be a stationary point of inflection coming up like that. And then I'm thinking that this third one over here, so that was my second equation in red, and this third equation here for my piecewise function. It's going to start here. It needs to have a derivative of 0 at that point because I've defined that point as a stationary point of inflection. So this will be a stationary point of inflection here, and then I'm thinking it's going to go up to a maximum here and then come down. So that's just kind of like putting together these pieces of information and sort of telling a story. So that's step one, sort of draw an idea of what you want your function to look like. And there are more than one possible way of answering this. You could have done this in several different ways, but this is how I sort of envisage it. I would say we have a minimum, then we have like a stationary point of inflection here and another one there. Stationary point of inflection continued for the blue function because the derivatives need to line up, maximum, and then coming down to a turning point there. Okay. So now that I've got these ideas here, let's list them out. So I'm going to need to come up with my three functions. In the end, my equation is going to look vaguely like the following. It's going to say, okay, we've got a name for the function. Let's call it f. It's going to have its domain, which is, as we can see, -2 to 6. We're told that those are its endpoints, -2 and 6. So we can say it's from -2 to 6 to r, and it's going to have the rule f of x is equal to, and we're going to define it like so. So to work out what the first function is, I'm going to call the first function f1 of x, just like I did last time. If we consider this curve here, it's useful to ask ourselves, what do we actually know about this first function? Well, we know three things about this first function. We know that the point -2, 0 lies on it. We know that the point 0, -4 lies on it, and we know that 0, -4 is a minimum. So given that we have three pieces of information, we're going to need to solve for a polynomial that has three unknowns in it, and that would be a quadratic. So this is kind of the procedure that you can think about. So we've got this function here. It's going to look something like that. So a quadratic equation has the form ax squared plus bx plus c. All right, let's now consider, before we even go about solving that, well, maybe let's list out what we know about it, right? So like I said just then, f1 of x, it meets the following criteria. We know that, so I guess let's write out initial conditions. Initial conditions, they are the following. We have that f1 of 0 is equal to 4. We have that f1 of -2 with an input of -2 is equal to 0. And we also have that the derivative function at point 0 is equal to 0 because there's a minimum there. All right, moving on to the second curve. So if we work this one out, we're going to say, okay, the second function, f2x, is going to have these points here. Now, like I said, I need that point there, 0, -4. I need that to have a derivative of 0 because it's an endpoint. It needs to be smooth with this black line here. So that's one point. We also know that that point lies on the curve, so that's a second piece of information. And with this other point up here, 1, 0, we know that that lies on the curve, and we know that the derivative is equal to 0, because that's how I've defined it. So again, that's four pieces of information. Because I have four pieces of information given to me, I need four unknowns to solve for. So therefore, I'm going to have to use a cubic. So this is going to be ax cubed plus bx squared plus cx plus d. And once again, let's just write out what those initial conditions are. Ooh, it's not working. Why is that not working? Maybe I need to scroll down a bit. There we go. Initial conditions, what are they here? Well, we have that. That point lies on the curve, so 0, -4. So we have that f2 of 0 is equal to -4. I think that should have been a negative sign there, right? And similarly, the derivative at 0 is equal to 0 because that is a minimum for this function as well. Our third point is that this point lies on the curve. So f2, 1. Ooh, stylus is playing up a little bit. So f2 of okay, that's definitely playing up a little bit. That's kind of frustrating. I don't know why that has happened. Let's try this like this. Okay, that's weird. I think I can't get rid of that point there for some reason. That's a little bit frustrating, but that is okay. F2, 0, so that is, oh, that's just appearing there on the screen. Wonderful. I don't even know how that happened. That's all good. That's all good. Let's just move on. So F2, 0, that was equal to -4, as we can see. So that's because this point lies on the curve. We also have that the function, so this second function here, at the points 1 is equal to 0 because the point 1, 0 lies on the curve. And lastly, this point here, F2 of 1 is a stationary point of inflection, so its derivative also needs to equal 0. So those are my initial conditions for that blue curve. Finally, for the third curve, so for f of 3, maybe we can start by listing out the initial conditions. It might help you come to think about this type of question. So, and again, like I said, we count up how many initial conditions we have, and then we can use that to work out what type of polynomial we need to construct. So this curve here, we can say that, okay, it needs to be smooth and continuous at 1, 0. So that tells us that f3, 1 needs to be equal to 0, and the derivative needs to be equal to 0 as well, because that point is a stationary point of inflection. Also, this point here, 4, 2, similarly is going to be a stationary point, so derivative needs to be 0 there, and the function needs to be equal to 2 at that point. So we have f3 of 4 needs to equal 2, and the derivative at 4 needs to equal 0. And then the final piece of information we've been given is that the point 6, 0 needs to lie on the curve. So therefore, f3, 6 is equal to 0. And believe it or not, that is all you need to do in order to work it out. But what you do need to know as well is how to use your CAS calculator. So I'm not going to show you all of these. The procedure is exactly the same every single time, but let me just give you an example of, say, for example, working out the third one of these. Oh, by the way, now that we can see, we've found that the function f3 has 5 pieces of information given to us. Therefore, we need to use a polynomial that has 5 unknowns. So therefore, we should be thinking, okay, we need to use a quintic polynomial. If there are 5 unknowns given to us, we need to, a quartic polynomial is what we should reach for. That's because when we write out the general form for a quartic polynomial, we have ax4 plus bx cubed plus cx squared plus dx plus e. We can see that there are 5 unknown values there that we're solving for, so therefore we can use these 5 initial conditions to find those. You could also have figured out that this blue curve is a quartic because it has a stationary point of inflection which corresponds to a power of 3, and then we have this so that's a power of 3 root, because it's touching and going through the curve at this x-intercept, and this x-intercept over here is a touch and go through. So that's a linear root and then a cube root. So therefore, overall, this must be a quartic. 2 different approaches to answering the same question. But let's see if we can figure out what this one is, and you can do the other ones yourself as like an exercise. So again, I'm going to step you through it. Basically, we go define, probably best to clear all before we do this. We can go define command, action command define. Okay, so we want to do this for f3, so I'm going to call it f of x is equal to ax to the power of 4 plus b times x to the power of 3 plus c times x to the power of 2 plus d times x plus e. There it is. I also want to define its derivative, so let's just make sure we get this right. If I define, say, g of x as the derivative, this is going to be equal to 4 times a times x cubed plus 3 times b times x squared plus 2 times c times x plus d. Okay, defined like that, and just double check. Sometimes it might be good to check you're working out there. I'll just try and power through it now. I've got the 5 initial conditions, so I'm going to create 5 rows here. And let's just write them out. We know that the function at the point x equals 1 is equal to 0. The function at the point x equals 4 is equal to 2. The function at the point x is equal to 6 is equal to 0. And then the derivative function, g, is equal to 0 when x equals 1, and the derivative function is equal to 0 when x equals 4. solve A, B, C, D, and E, hit enter, and it tells us this is our answer. So hypothetically, if we did everything correct here, we should have that, at least for that third function, at least for this third function here, we should have that f3 is equal to 54 x to the power of 4 minus 1 over 3 x to the power of 3 plus 31 over 18 x squared minus 68 over 27x plus 10 over 9. And don't forget, so I'll just put this here, plus 10 over 9. And don't forget to specify the boundaries. So for this particular boundary, that'll be defined from x is equal to 1. So x is equal to 1 right up until x is equal to 6 for that first one there. Similarly, for the black boundary, or that black one there at the start, we should have whatever the function we come up with following the exact same procedure will be defined from x is equal to -2 up to x is equal to 0. Yep. And then the red function here is going to be defined from x is equal to 0 right up until, so let's define it on that side. So right up until x is equal to 1. All right. There we go. So something along those lines, you'd work out each of those functions using that method that I showed you, and then you would need to work out what your overall equation is. The answer for this particular function I worked out before this video, so this is one potential solution. So the first function will work out to be x squared minus 4 for that quadratic, and then that cubic part in the middle there is -8x cubed plus 12x squared minus 4. All right, and that's just showing you. It's always good to double check your answer at the end. So graph this on the CAS afterwards just to make sure that your function is indeed smooth and continuous. It's very easy to make mistakes somewhere along the line here, as you saw just before. So yeah, always good to graph it, double check, do all of the points line up. Does the graph look smooth and continuous? If I zoom in on this point here, the derivative does appear to be quite smooth there. There doesn't look to be any jagged edges. It comes to a derivative of 0 here. And then the red, the green function there also has a derivative of 0 from that point. So that's how you would approach this sort of question. And like I said, there will definitely be questions like this on the SAC that are open-ended. So see if you can work them out. And as a final little question to you, an extension to this question, which may or may not be in the SAC, might be, okay, we've defined this function using a piecewise graph, but what if now we want to find a single polynomial function that could be used to describe all of these points, and we could get given new initial conditions, say we want this to be a minimum, so that needs to be a stationary point, that needs to be a stationary point, that needs to be a stationary point. How many initial conditions is that so far? Well, 3 points. And then the fact that their derivative is equal to 0, that's already 6 initial conditions. And then we've got 2 more points. So let's say we want all of those points to lie on the function and we want to describe it with a single polynomial. We have 8 initial conditions. What order polynomial would you need to define in order to find what those values are, and how do you go about doing it? So that's an extension question to you. But yeah, that could definitely be a follow-up to this sort of problem. All right, hopefully that was helpful for you guys. Thanks for watching, and I'll see you guys next time. Have a good one.